This supplementary video introduces GeoAlign, a proposed state-guided spatial alignment architecture for VLA policy learning. We begin with a preview of GeoAlign's state-guided geometry attention in a real-world transparent container task. The left side shows RGB observations, and the right side shows geometry query attention maps. They illustrate the core idea. During execution, the policy should attend to local regions such as the container boundary, held object, gripper, and action area. Fine-grained manipulation requires geometry-aware spatial alignment beyond semantics. During approach, alignment, and insert or release, the task-relevant region shifts with the robot state. This is especially challenging for transparent or annular objects, where RGB may preserve object boundaries but measured depth can be missing. The key gap is dynamic selection. Continuous action decoding needs a compact way to select execution-relevant local geometry as manipulation progresses. To address this gap, we propose GeoAlign, a state-guided spatial alignment architecture for VLA policy learning. The first stage is geometry post-training. GeoAlign post-trains a depth anything v2 small geometry branch with robot domain RGBD supervision, then discards the depth head and keeps RGB-derived geometry enhanced post-trained features or GEP features. During rollout, the policy still uses RGB, not measured depth, point clouds, or predicted depth maps. The second stage is GeoAlign policy learning. The frozen geometry branch produces an image space GEP grid from multi-view RGB observations, and proprioceptive state queries cross-attend to this grid to extract 8 compact, phase-dependent geometry tokens. These tokens are concatenated with RGB language tokens and condition the flow matching did action decode. We then show execution videos, starting with simulation validation on Libero and Fractal. In the real world, first, the robot places ice into a transparent bottle. We also test and scene scenes with additional objects as distractors, where the baseline often misaligns. Second, it inserts a small tape roll into a larger tape roll, testing annular alignment. The baseline can miss the ring opening. Third, it retrieves clear tape from a box partially covered by a plate, where the graspable region is partly occluded. The baseline struggles under occlusion. Then, we include an out-of-domain pickup example, where GeoAlign still performs well. Finally, it places objects around a plate, testing front, behind, left, right, and on top relations with only 10 training trajectories per relation task. Overall, GeoAlign reports 99.0% on Libero, 85.3% on Fractal, and 78.8% on real-world Aloha, compared with 65.0% for the real-world RGB-only baseline. The Libero ablation isolates where the gains come from. All variants share the same VLA backbone, decoder, training protocol, and checkpoint selection. Removing geometry post-training, replacing spatial querying with global pooling, or replacing state queries with learned queries all reduces performance. This shows that both RGB-derived geometry features and state-guided selection are important. Overall, GeoAlign adds state-guided geometry tokens to make VLA action decoding more spatially grounded. Thank you for watching.